Earlier on, we discussed what a cation and an anion is, and cations have a positive charge, and anions are ions with a negative charge. And ionic compounds consist of a combination of both cations and anions, and their charges will balance out in that ionic compound. So the formula is usually the same as the empirical formula. And again, the sum of the charges of the cations and the anions on each formula in each formula unit must equal 0. So let's take, for example, the ionic compound sodium chloride. You can see that we have this crystalline structure here in A, and you can see that we have the cations. So if we say here's our cations here and here's our anions, and you can see that an ionic compound does not exist as a molecule. So ionic compounds do not consist of discrete molecular units. So for example, a solid like sodium chloride consists of equal numbers of sodium cations and chloride anions arranged in a three-dimensional network that we call a lattice. And so we call this a lattice, and that is why when you look at sodium chloride, if you look at it close up, if you take some salt from a salt shaker and you look at it really close, it has a cubic shape. So it's important that you never call an ionic compound a molecule. I should also point out that ionic compounds are made from metals and nonmetals. Let's take our example of sodium chloride. Sodium is a metal, and you can see that it's found in group 1A, and that's a metal for sure. And chlorine is found in group 7A, or it's a halogen, and it is a nonmetal. And so ionic compounds, again, are made from the combination of metals and nonmetals. And on this slide here, we see some of the more reactive metals highlighted in green and some of the most reactive nonmetals, which are highlighted in blue. And you're going to see these elements combining oftentimes to form ionic compounds, just like we pointed out that you could have sodium chloride. Now, you could also have something like, let's say, calcium fluoride, right? Calcium fluoride. Now that would have a different formula, but again, you can see that ionic compounds are made from the combination of a metal and a nonmetal. Also, before we move on, I'll point out that the cations that are formed from metals, right? Metals will tend to form cations. The metals in group 1A like to form +1 charges. The metals in group 2A like to form +2 charges, and aluminum is in group 3A. It likes to form a +3 charge. On the other hand, the nonmetals like to form negative charges, and the halogens in group 7A, they like to form a -1 charge. The elements oxygen and sulfur like to take on a -2 charge, and the nitrogen likes to take on a -3 charge. And we need to keep these charges in mind when we're making ionic compounds, because again, the cation and the anion will have to combine in such a way that their charges balance out. So let's take a look at some practical examples here. Let's say we want to make an ionic compound from aluminum and oxygen. Well, as I just told you, aluminum likes to have a 3+ charge, and oxygen likes to have a 2- charge. How would I combine those so that I would cancel out +3 and -2? Well, I can't just have a 1-to-1 ratio, because if I add +3 and -2, I'm going to have +1. Okay, I'm going to have a charge of +1. So I need to balance that out. Now, the book has a little simple trick that they like to use, which is where you basically swap the quantity of the charge for the subscript. So you put the subscript, so what I'm saying is that you'd put the subscript 3 next to the oxygen, and you'd put the subscript 2 next to the aluminum. So when you balance that out to make Al2O3, which is shown right here, the charges will balance out. And if you're wondering, well, how do you know that? Well, remember, the charge of an aluminum is +3. So if you take 2 times 3, that equals +6. The charge of an oxygen is -2. If you take 3 of those, so 3 times -2 is -6. What do you get when you take +6 and you add -6 to it? You get 0. And so those charges balance out. Let's take a look at another example. Let's say we tried the same thing if we wanted to make a compound with calcium and bromine. Well, I told you that calcium is in group 2A. It likes to have a charge of +2. And bromine is a halogen. It's in group 7A. It likes to have a charge of -1. So again, you can either try the swap the quantity of charge. So we have we have a 2, so plus 2, and then we have a minus 1. The number 1 isn't written as a superscript, but we assume that. And so we would put a 1 next to our calcium and a 2 next to our bromine to make CaBr2. Again, the rationale is the exact same in that the calcium has a plus 2 charge, and if you take 1 calcium, so 1 times 2 is going to give you plus 2. And since the bromine has a minus 1 charge, you take 2 of those, so 2 times minus 1, and you get minus 2. What happens when you add plus 2 and minus 2? You get 0. They balance out. Here's another example. I noticed there was a little typo here. It said sodium 2+, but sodium, again, as I mentioned before, is in group 1A. It likes to have a charge of plus 1. And then we have what's called a polyatomic ion, and this is a cluster of atoms together. And when they're put together, the carbon and 3 oxygens, we call that carbonate, and it has a 2- charge. Well, how many sodiums would I require to balance out the 2- charge? Well, if there's only a plus 1 charge on the sodium, I'll need 2 of them. And so when we put all of that together in our formula, we get Na2CO3. So the take-home message from this slide is, again, we have to combine our cations and our anions in such a way that the charges are going to balance out in our ionic compounds. Let's take a look at a quick problem here. It says, write the formula of magnesium nitride. Well, magnesium, hopefully you know the atomic symbol for magnesium, and nitride comes from nitrogen. Okay, so from nitrogen. Now, hopefully you remember that magnesium was in group 2A, the alkaline earths. And so it has a 2+ charge, and nitride has a 3- charge, and I pointed that out a couple of slides ago. And so if we want to make an ionic compound, we have to combine this magnesium and this nitride in such a way that the charges are going to balance out. Now again, you can use the book's trick where he swaps the quantity of the superscript. So he swaps the 2 and the 3, so you write Mg3N2, and that would be magnesium nitride, and that is the correct answer. Now, you might be wondering, again, why is that the correct answer? Well, let's think about it. We have 3 magnesiums. So for our magnesium, we have 3 times positive 2. So 3 times positive 2 gives me positive 6. And for our nitrogen, for our nitride, we have a charge of -3, but we only have 2 of those. So 2 times -3 gives you -6. What happens when you add up positive 6 and -6? You get 0. And so that is the correct formula for magnesium nitride. So again, I'm just going to point out that you have to have memorized the charges of the alkali metals in group 1A, the alkaline earths in group 2A. Aluminum has a +3 charge, and then the other nonmetals, the halogens, like to take on a -1 charge. Oxygen and sulfur have -2 charges, and nitrogen likes to have a -3 charge. Let's get into what's called chemical nomenclature. And nomenclature is just a tsatsi name for the way that we name chemicals in chemistry. So first we're going to take a look at how to name ionic compounds. We've already defined what an ionic compound is, and it's the combination of a metal and a nonmetal. And what we have to do is we have to take our anion, which is our nonmetal. So for example, in sodium chloride, chlorine is a nonmetal, and we add "ide" to the end, right? So we always add "ide," I-D-E, okay, as our suffix. So you can see that in this compound here we have barium, which is our cation. The cation remains unchanged, okay? And then we have chlorine, Cl, right? Chlorine, okay? But again, in an ionic compound, we change the anion suffix to "ide," so it becomes barium chloride. Let's look at the next example. The cation always remains unchanged. So we have just K, which is potassium, and then instead of oxygen, we put the suffix "ide," and so it becomes potassium oxide. Let's look at the next one. The next one employs a polyatomic ion. I'll help you out. You'll have to have this polyatomic ion memorized. This is hydroxide, and the only way to know that is to have it memorized, so you must memorize that polyatomic ion. So we have magnesium. Again, our cation always remains unchanged, so simply magnesium, and then hydroxide. So that shows you that you have to have the polyatomic ion memorized. Here's another example where we have a polyatomic ion. Again, we have K, which is our metal, which is potassium, and then we have NO3, and NO3 has a -1 charge, and that's called a nitrate. A nitrate. And so this becomes potassium nitrate. And so it's very important that you memorize the polyatomic ions, two of which are shown here, the nitrate and the hydroxide, and we're going to look at those in greater detail soon. Now you probably remember that earlier on in the class I mentioned how the transition metals, the metals that are found down here in group from 3B to Now earlier on I mentioned the transition metals, which are the metals that are found down here from group 1B to 3B. So these are the transition metals right here. And the transition metals, most of them can take on more than one charge, except for silver, zinc, and cadmium, and I went over those exceptions with you. So say, for example, you have iron, and iron can either adopt a +2 or a +3 charge. Now it says here that when you make a transition metal ionic compound, so one where the metal is a transition metal, you have to indicate the charge on the metal with Roman numerals. So if the charge is +2, you simply use the Roman numeral 2, so for +2. If the charge is +3, you use the Roman numeral 3. Pretty simple, right? Anyhow, so you might be asking, well, how do I know if it's +2 or it's +3? Well, what did I tell you earlier, okay? Hopefully you noticed that these two compounds, okay, FeCl2 and FeCl3, both have chlorine in them, okay? And remember, when chlorine is found in an ionic compound, the chlorine takes on a charge of -1 and becomes a chloride. That never changes, right? Cl is always going to be Cl -1. So if I have two chlorides here, right, that means I have overall 2 times -1, which would give me -1. So that means, -2, which means that the iron has to be a +2. Okay, that's our rationale. The same thing applies to FeCl3. Chlorine, again, when it's in an ionic compound, it's chloride. It has a charge of -1, but there are 3 of them here. And so if we have 3 chlorides, that gives us a charge of -3 overall. And so our iron has to be +3. And that's how you determine the charge of the transition metal, is by looking at the nonmetal, whose charge does not vary. Okay? And so the way we would name this compound is, you might think, okay, well, both of these would be iron chloride. Well, remember, you have to indicate the charge of the metal with Roman numerals. And so FeCl2 becomes iron 2 chloride, and FeCl3 becomes iron 3 chloride. Let's take a look at this example shown at the bottom. We have this interesting compound here, Cr2S3. Hopefully you remember that sulfur always has a 2- charge. That does not change. Now if I have 3 of them, 3 times -2 is going to give me an overall charge of -6. And I have 2 chromiums. Okay? Now I need an overall charge of +6 here to balance out my -6 from my sulfide. But if I take +6 and I divide it by 2, that means each chromium is going to have a charge of +3. And so the charge on my chromium is 3, and therefore the name of the compound would be chromium 3 sulfide. This naming system, where we put the charge of the cation or the metal with Roman numerals in brackets, sometimes this is referred to as the Stock naming system, named after a German chemist named Alfred Stock. This slide kind of rehashes some of what I've taught you already, but remember, the ions in group 7A form a -1 charge. The ions in group 6A have a -2 charge, in group 5A a -3 charge, and in group 4A a -4 charge. And so we add "ide" as a suffix to any of these elements. And so fluorine becomes fluoride, chlorine becomes chloride, bromide, iodide. If we look at group 6A, we have oxide and sulfide. Those are very common in our class. Selenide and telluride won't come up as much, but they can come up from time to time. In group 5A, I'd say that nitride and phosphide are very common in our class. And then in group 4A, carbide and silicide, they come up from time to time, but not nearly as common as the ones that I have highlighted in yellow. So again, you add "ide" as a suffix to your nonmetals when you're naming monatomic anions. Okay, so it takes a lot of time, but you have to have all of the ions in table 2.3 memorized. And it's a big table, so let's take a look. Some of them are pretty evident, like if we start with a cation aluminum. The next one is a polyatomic cation, which is ammonium, so NH4+, you have to know that. Then we have barium, cadmium, calcium, cesium. We can have chromium-3. There's an older naming system where you use chromic and chromis and all these different things. I'm not going to focus on that in this lecture, so chromium-3 would be chromium with a 3+ charge. We have cobalt-2, so this is supposed to be a number 2, not the letter U. Anyhow, cobalt-2, we have copper-1, copper-2, a hydrogen ion, sometimes we call that a proton. Iron can take on a +2 or a +1 charge. Again, the older system uses ferrous and ferric, but I'm not going to focus on that in this lecture. Then we have lead, which can take on a charge of +2, lithium, magnesium. Let's take a look at the anions over here. So we're going to start with bromide. Now, carbonate, you have to have carbonate memorized, CO3, which has a 2- charge. Chlorate, which is Cl O3 -1, so chlorate, then chloride. Chromate, which is CrO4 2-, you have to have that one memorized. Cyanide, same thing, Cn-1. Dichromate is Cr2O7 2-. I'll just point this out. Students sometimes struggle with the difference between chromate and dichromate, but you have to know both of those. It's handy to make flashcards maybe. Dihydrogen phosphate, which is H2PO4 with a -1 charge. Fluoride. When a hydrogen has a -1 charge, it's called a hydride. We have hydrogen carbonate or bicarbonate. Either one is used in this class for HCO3 with a -1 charge. Hydrogen phosphate, which is HPO4 with a -1 charge. Hydrogen sulfate or bisulfate, either one is acceptable for HSO4 with a -1 charge. Hydroxide, I showed you that one earlier in this video. Iodide and nitrate, we also talked about that earlier in this video. Let's keep going and get back to cations like manganese 2, so manganese 2, mercury 1, mercury 2, potassium, rubidium, silver, sodium, strontium, tin 2, zinc. What else? We've got the nitride, the nitrite. So in the last slide, we talked about the nitrate. So remember NO3 -1, that's nitrate. And when you lose an oxygen to NO2 -1, it becomes nitrite. Then we have an oxide. Then we have permanganate, which is MnO4-. Peroxide, phosphate, which is PO4 3-. Sulfate, which is SO4 2-. Sulfide, sulfite, the same thing that we saw with the nitrate and the nitrite, is that when you go from 8 to 8, you lose an oxygen, going from sulfate to sulfite. And thiocyanate, which is SCN-. All right, so you have to know all of those anions and cations, and many of them are polyatomic, like things like phosphate and sulfate and sulfite and so on and so forth. So those are important to have memorized for the first exam. Let's take a look at this example here. This is example 2.5. It says name the following compounds. And in order to name these, you have to be able to recognize some polyatomic ions. So let me just write down what I recognize right away. In A, I notice we have copper, right? We definitely have copper. What else do we have? We have NO3. And NO3 has a -1 charge, and it's called a nitrate. Okay, it's a nitrate. Now, again, that nitrate has a -1 charge, but there are two of them. Okay, so if I take 2 times the negative charge, the -1 charge of a nitrate, that gives me overall a charge of -2 over here. So that tells me that my copper must be +2. And so the way that I would name this compound is, since copper is a transition metal, I would say that this is copper 2 with my Roman numerals, nitrate. And so one of the take-home messages here for me as your instructor is that you as a student have to be able to recognize a polyatomic ion when you see it. Let's take a look at B. And this is another polyatomic ion over here. We have K, which is potassium, so that's not too bad. And potassium is in group 1A. It only has one charge, which is a +1 charge. But then we have this big polyatomic ion here. And again, that's one that you're going to have to recognize, okay? It's H2PO4 minus. And that is dihydrogen phosphate. So dihydrogen phosphate. Okay, so you have to have that one memorized. Now, since potassium is not a transition metal, we do not have to put a Roman numeral. Potassium is in group 1A. It only has one possible charge, and that's +1. And so when I put this all together, I get potassium dihydrogen phosphate. All right, and let's give the last one a try. So the last one, C. Oh, wow, there's two polyatomic ions in this one. And you have to be able to recognize these. NH4 and also ClO3. Those are both polyatomic ions. Now, the only way to know those is to have them memorized. NH4 has a +1 charge, and it's an ammonium ion. So ammonium. And ClO3, hopefully you remember, that has a -1 charge, and it's called a chlorate. Chlorate. And so the answers to these three compounds are copper 2 nitrate, potassium dihydrogen phosphate, and ammonium chlorate. Is there a lot of work here in memorizing these? Oh, absolutely there is. Absolutely. Okay? But it will be very rewarding in this class when you are able to name compounds quickly and effectively. It will help you be able to communicate with other scientists a lot more effectively and help you to understand what you're reading and what you're hearing throughout the course. Okay, let's take a look at example 2.6, which basically flips example 2.5 around. It says we're going to write chemical formulas for the following compounds. So the first one is mercury nitrate. They're getting kind of tough with us right off the get-go because mercury 1 is kind of an interesting cation, and it is in the table that I showed you earlier, and maybe you didn't notice, but mercury 1 is not simply Hg plus like that, it's Hg2 and 2 plus like that. So you have the two mercury atoms together, they're bound together, and then they have a 2 plus charge. So that's mercury 1, and then nitrite is NO2 minus 1. And so I'm going to have to put two of those nitrites together to make my mercury 1 nitrite balance out. And so the formula, the formula for this ionic compound would be Hg2. And then since I have two of my polyatomic ion, I have to put an open bracket right in the polyatomic ion, and then I put a subscript outside of that, which indicates that I have two of them. Let's take a look at B. We have cesium sulfide. Cesium sulfide, so cesium is in group 1A, so cesium always has a 1 plus charge, and sulfide always has a 2 minus charge, and I went over that earlier in this video. And so I'm going to have two cesiums to cancel out the -2 charge, and so I get CS2S. And let's give the last one a go. The last one is calcium phosphate. Calcium is in group 2A. Calcium always has a 2 plus charge, and phosphate is a polyatomic ion. It's PO4 3 minus. How did I know that? I have it memorized. And again, this is one where you can try that trick. And I guess you could always try the trick where you swap the quantities of the charges and use those as subscripts. Okay, so it would be Ca3 PO4 2. You could do that, or you could try to balance out the charges. I like to just think about balancing out the charges. If I have a 2 plus charge on my calcium and a 3 minus charge on my phosphate, how would I balance those out? Well, I would use 3 calciums to give me +6 and 2 phosphates to give me -6. Either way works, but regardless, what you're going to end up with, no matter what, is you're going to end up with Ca subscript 3. That indicates that you have 3 calciums. And since we have a polyatomic ion, PO4 3 minus, I have to put the whole polyatomic ion in brackets like that. And then I need 2 of those to make -6 overall. And so I put the subscript 2 outside to make my formula for calcium phosphate.